Thanks for the introduction. So yes, I'm Eric Jollès from EPFL, and this is joint work with my colleagues from NIM and MPI-SP. So when Alice is browsing internet, her traffic might be encrypted, but her IP header is not. So anyone on the link can be her boss, intelligence ISPs, or just anybody curious can see the source and destination IP address, and then can infer that Alice visited a website. For this reason, we have nowadays anonymous communication network that should at least hide the IP header, so no one can know directly that Alice is browsing example.com, but an adversary that sits between Alice and the anonymous communication network can still observe the timing, the size, and the direction of packets. With this, the adversary can train a machine learning model that will be able to predict which website Alice browsed. And yeah, so this is what we call website fingerprinting attacks. And this is a threat we are studying in this project. And we are the first one to study this threat on the NIM mixnet. So NIM was originally built to send messages, and it was adapted to be able to browse internet with it. So how does it work? Alice will send a packet to a proxy that will be sent then on the mixnet with 3 different mix nodes, will reach the requester, and then the requester will redirect the request of Alice to the browser and then send back packets to Alice. And to hide the traffic, NIM is using 4 different mechanisms that are quite important to understand right now because yeah, the paper is about that. And the first mechanism is called mixing delay. So a packet that enters the mixnet will go through 3 different mix nodes. And at each mix node, the packet will wait for a random amount of time. By default, it's close to 50 milliseconds, and go to the next mix node. And the goal of these mechanisms is that if an adversary sees like a packet going out of a mix node, it will not be able to know like to which in packet that entered the mix node it's related to. The second mechanism is called loop cover traffic. So Alice will send as a background process packets to herself via the mixnet. She will send these packets at a steady rate. So by default, they will be separated by approximately 200 milliseconds and still like random time between the packets. Up. And this creates some background noise that should hide the activity of Alice. The third mechanism is called the client Poisson rate. So the goal of this is like when Alice has real packets to send, she will send them at a steady rate. So these packets can be, for example, HTTP requests. So similar way as before at steady rate, so 20 milliseconds by default. And when she does not have any packet to send, she will send instead some loop cover traffic. And the steady rate will make should hide the timing pattern of the real activity. And the loop cover traffic should hide when Alice is really sending packets or not. And the last mechanism that we'll present is the requester Poisson rate. So it's similar to the client one, but from the requester to Alice. So when packets arrive from the browser, they will go through the request that should send them at a steady rate. But this mechanism is off by default because keeping a link for every user by the requester is quite costly, and also it will flood the mixnet. So it was decided to not use it. And that will be one of the issue of the browsing in NIM. So we will see that in a minute. And so with this 4 mechanism, we have some research questions. So do this mechanism actually stop website fingerprinting? Then we will ask if these mechanisms are beneficial or if there are some that are also detrimental. And to finish that, can we build stronger defenses without modifying the NIM mixnet? So to know if NIM can be fingerprintable, we will take a look at how the traffic look like. Here you can see on the green, on the bottom left of the screen, the number of packets sent by second. So these are the packets that goes from Alice to the proxy. And here we can see there is no real pattern. We cannot really know when she's sending or not. So the cover traffic is really doing its job well. However, on the other side is quite different. So the browser will send bursts of traffic to the requester, and then that should go to Alice. But as I said before, there is no constant rate at the requester side. So the burst of packets will go directly to the mixnet, so it will be delayed by the mixing delay. And what we have at the end, because there is just a delay added to the packets, we'll have the same burst, but shifted and spread it out. And we can see that there is still like a pattern that exists. And this pattern, as this number shows, can still be used to make the website fingerprinting attack work. So here, 0.87 is quite high, like 1 is considered as perfect classification, and it's with the TikTok attack. So it's quite close to what Tor is providing. So Tor is close to 0.95 in our captures. And it comes with a very high bandwidth overhead. So yeah, a lot of overhead for not that much gain. So we just saw that just adding the mixing delay does not really help. And yeah, because it will just shift and delay the burst of traffic. And we wanted to know if this mixing delay was beneficial or detrimental. And what we notice when we remove the cover traffic is that having a small mixing delay provides better defense than having a big one. And the reason of that is that the burst of traffic, when you have big mixing delay, you will have bursts that are more separated in time. And if they are more separated, you can, like they are more identifiable by the machine learning model, and then like it will provide better score. Yeah, so mixing delay does not really help. So the other mechanism that we can use to protect the traffic is the requester Poisson rate that is off by default. And when we turn it on, we have some improvement in the F1 score. So it goes to 0.75, which is better, but still like not as good as some Tor defenses, for example. And it comes with a very high bandwidth and latency overhead. Yeah, so the reason of that is that when the requester is sending cover traffic, the cover traffic will be looped back to the requester, but will never reach Alice. So the adversary that is the Alice to the proxy link will not see any cover traffic and will still be able to know when there is traffic or not, and this is enough to make some classification. And so the first question, defense we propose is like just to have the cover traffic that reaches Alice, and this is what we call Poisson. Yeah, so it will send it at a constant rate, and it gives near total protection, but still has a lot of overhead. So this is overhead compared to vanilla lim. So it's higher than lim that is already high. And the second defense we propose is the one that will have less overhead. The goal, like how this defense works, so we will add some fake burst in a similar way as WTF pad. So this burst are learned from a real burst, and then the adversary will struggle to find patterns, and the F1 score drops to 0.39, and we'll still have like some bandwidth overhead because of course we add the burst, but very limited if you compare it to the Poisson, this one that was very high. Yeah, so to conclude, yeah, so NIM was first designed for messaging, and it does not really translate to a good defense for web browsing. We show that with like adapted defense, we can still use NIM properly to hide the traffic with WTF for NIM for like low overhead and Poisson for near total protection. And yeah, we still have a lot of more results in our paper, and we will be very happy to discuss about them in the poster. Thank you for your attention.